So hello and welcome back to the class on algorithms. In this video we are going to discuss one important problem in computer science, namely sorting. In this video we will consider given a sequence of number, how to sort these numbers in the increasing order. So the same technique can also be generalized to sorting objects as long as there is a well-defined partial order defined on the objects. So what's a partial order? Given two numbers, there is a function, let's say is less than, which takes two objects and returns true or false. If it returns means that x is smaller than y, otherwise y is smaller than x. If there is, as long as there is a function which there is a well-defined way of deciding two objects, comparing two objects, these methods generalize. So we will assume that for simplicity we will assume that the given sequence of numbers are integers and try to sort them in the increasing order. In this video we are going to study bubble sort, selection sort and insertion sort. The complexity of these algorithms are order n square. These are not very efficient algorithms. In the later part of the videos we are going to see merge sort, quick sort and heap sort. All these algorithms the sorting can be done in n on n. So we at some point of later in the course we are also going to see that any comparison based algorithm, that is any algorithm which sort the given sequence of numbers only based on comparisons, would require n log n number of comparisons. In other words, any sorting based algorithm, comparison based sorting algorithm has a lower bound of n log n. In that sense, the merge sort, quick sort and the heap sort algorithm that we are going to study are optimum sorting algorithms. To begin with, let's start with the easy ones. We will start with bubble sort, selection sort and insertion sort in this video. So in this video we will be studying sorting algorithms. More specifically, in this particular video we will be studying bubble sort, selection sort and insertion sort. In the next feature videos we will be talking about merge sort and randomized quick sort. Before we get into the sorting algorithms, let's try to understand what's a sorting problem. So we are given a sequence of numbers, let's call it as a0, a1, a of n minus 1. There are n integers that are given to us. We want to arrange in the increasing order such that the smallest number is in the beginning and the largest number is at the end, such that a of 0 is smaller than or equal to a of 1, smaller than or equal to a of 2 and so on, so which is smaller than or equal to a of n minus 1. Let's look at the first simplest algorithm to solve this problem. This is called a bubble sort algorithm. In the bubble sort algorithm, you compare two consecutive numbers. Let's say a of j and a of j plus 1. Since we are trying to sort the sequence in the increasing order, we expect a of j to be smaller than or equal to a of j plus 1. If this condition is not true, in other words, a of j is greater than a of j plus 1, that means that these two numbers are not in the order that is required. In that case we swap them, right? So we'll repeat this from all possible values of j, from j is equal to 0 to n minus 1. Okay, for j is equal to 0 to n minus 1, if a of j happens to be greater than a of j minus 1, then we keep swapping all these numbers. So at the end of this algorithm, what really happens is that the largest number moves to the location a of n minus 1, right? So why is that true? So when you compare the largest number with any other number, if the largest number is on the left hand side, then it will be swapped. If it is at any location, once you hit the largest number, if it is on the left hand side, it will always be swapped with the right side. So eventually the largest number will move to the end. Once the largest number has been moved to the end, so what we do is that in the future iterations we just ignore the last number and repeat the same algorithm and the rest of the sequence. So the code for this will look like there will be n minus 1 iterations. When there is only one number left, we don't do anything. In the remaining n minus 1 iterations, in the ith iteration, we consider the numbers from 0 to n minus 1 and compare a of j to a of j plus 1. If these two, if a of j is greater than a of j plus 1, then we swap these numbers. So in one iteration, the largest number goes to the a of n minus 1 location. In the second iteration, the second largest number goes to the a of n minus 2nd location, and in general in the ith location, the ith largest number goes to a of n minus 1 minus I. So at the end of these operations, because in each iteration we are considering all the numbers, and among all the numbers that is considered, the largest number is pushed to the rightmost end, this algorithm sorts the given sequence of numbers. Let's try to understand what is the time complexity of this algorithm. Less Tn is the number of comparisons done by the bubble sort algorithm. So initially we do n minus 1 comparisons and to push the largest number to the end. After that we repeat the same thing on the remaining n minus 1 numbers. So the recursion that we get will be t of n is equal to n minus 1 plus t of n minus 1. So this turns out to be, if you expand this, you get n minus 1 plus n minus 2 plus n minus 3 and so on. This is basically the sum of the first n minus 1 numbers, whose sum is equal to n into n minus 1 by 2, which can be written as theta of n square. So if t of n is the number of comparisons done by the algorithm, the bubble sort algorithm, then the complexity of this algorithm is theta of n square. Let's also try to understand the number of swaps done by the bubble sort algorithm. So if the given sequence is already in the increasing sequence, then the algorithm doesn't do any swaps. It still does theta of n square number of comparisons, but it doesn't do any swaps if the sequence is already in the increasing order. But if the sequence is in the decreasing order, then that's the worst case. So the first number is the largest number, so it has to be pushed to the end. So the number of swaps that you will end up doing is n minus 1. Okay, and the same thing is repeated for the rest of the sequence. This should be t of s, right? So n minus 1, if you expand this again as before, so you get that this is equal to theta of n square. So in worst case, the number of swaps done by the algorithm is theta of n square. So in this video we have seen what's a bubble sort algorithm. It's a very simple algorithm. You just compare two consecutive pair of numbers. If they're not in order, just swap them. In one iteration you'll push the largest number to the end and then work on the remaining n minus 1 numbers again repeatedly. So we have seen that in any case this algorithm does n into n minus 1 number of n into n minus 1 by 2 number of comparisons. So the complexity of the algorithm is theta of n square, and we also looked at the number of swaps done by the algorithm. The number of swaps done by the algorithm can be 0, or it can be again as bad as n into n minus 1 by 2. In worst case, the number of swaps is also theta of n square. So notice that in each of the iteration of the algorithm, the only thing that we achieve is to push the largest element to the end. If the objective is to push the largest element to the end, do we really need to do n number of swaps, odd n number of swaps? Probably we need to do odd n number of comparisons, but odd n number of swaps may not be required. This is precisely what is exploited in the next algorithm, which is called the selection sort algorithm. In the selection sort algorithm, we will try to ask the question, if the aim of the algorithm in one iteration is to push the largest number to a of n minus 1, do we need to really do n minus 1 swaps? So probably this is not required. So you can just look at this simple code. So what it does is that it finds a location where the largest number is there, and if it is not in the last location, you just swap it with the last location. I repeat, find the location where the largest number is there, and then if it is not at the last location, just swap the last number with the location where the largest number is there. So we will assume that the largest number right now is the first one. Then from j is equal to 1 to n, if a of j is bigger than the largest number that we have seen so far, that is at a of max, then you set the index of the largest number as max is equal to j. At the end of this algorithm, so max will tell you the location where the maximum number is there. If this is not the location which is same as the last location, then you swap these two numbers. So we are doing n minus 1 comparisons here. At the end of this comparison, so what we really have is that the location of the largest number, and if it is not the last location, then we swap the location of the largest number with the last number. So if you just repeat this, so what we have done in one iteration, the inner loop, what it tries to do is that it tries to push the largest number to the end. So once the largest number goes to the end, you just repeat the algorithm again with the n minus 1 number of iterations. In the ith iteration, you just look at the first n minus 1 minus I numbers. In the ith iteration, you are just looking at the numbers from 0 to n minus 1 minus I, and the inner jth loop will try to find among all the numbers from 0 to n minus 1 minus I, it will find the location of the largest number. So once the location of the largest number is found, if the location of the largest number is not n minus 1 minus I, then swap the largest number location with the largest number with the n minus 1 minus ith location number. Okay. So as seen, the correctness of the algorithm follows from the correctness of the bubble sort algorithm, because in each iteration among all the numbers that we are considering, we will push the largest number to the end. So let's come back to the number of comparisons done by this algorithm. If that is defined as t of n, as before, this will be t of n is equal to n minus 1, because so in order to find the maximum among all the n minus n numbers, we need to do n minus 1 comparisons. That's what we do. After that, we work with the remaining n minus 1 numbers. So the recursion that we get will be t of n, which is equal to n minus 1 plus t of n minus 1. So if we expand this, what you get essentially is n minus 1 plus n minus 2 plus n minus 3 and so on plus 1, which is essentially the sum of the first n minus 1 numbers whose sum happens to be n into n minus 1 divided by 2. So the total number of comparisons done by the selection sort will be exactly equal to theta of n square. But you will see a large improvement over the number of swaps done by the algorithm. In the best case, when the sequence is already sorted, in this case the largest number in the first iteration is already at the end, so you need not do any comparisons, swaps. So the total number of swaps done by the algorithm, if the sequence is already sorted in the increasing order, is 0. But if the sequence is already not sorted in the increasing order, so in worst case what may happen is that the largest number may not be in the right place. So in each of this iteration we may have to do one swap. So you get the equation that t of n is equal to 1 plus t of s of n minus 1. So if you expand this, so what you basically get is this is equal to n minus 1. So the number of swaps done by the selection sort algorithm in worst case is theta of n. So in summary, what we have seen is that both algorithms, the bubble sort and selection sort, in any case will do order n square number of comparisons, but the only difference is the number of swaps in both the cases will be different. In worst case, the bubble sort algorithm will end up doing order n square number of swaps, but that is only linear in the case of a selection sort. In the next algorithm that we are trying to see, which is insertion sort, we will try to avoid doing the swaps. The main idea here is that in the case of both bubble sort and selection sort is that we are trying to push the largest element to the end, then work with the other sequence. Now in the case of insertion sort, we will try to work around the other way. We will assume that the first n numbers or I numbers are already sorted, and we will consider the I plus 1 number and try to ensure that the I plus 1 number in the next iteration will be sorted. This is by inserting the new number that you are considering into the right place in the sorted sequence. How exactly to do it? So what is the complexity of this algorithm? Let's continue to see this in the rest of this video. So in order to consider this insertion sort algorithm, let's first ask the question. You are given a sorted sequence and you are also given a number. You want to insert this into the sorted sequence. Okay. Let's say that the given sorted sequence is 2, 10, 13, 18, 24 and 58. So the 14 will be actually here in the next location. Okay, so we want to insert 14 into the sorted sequence. So what I do is that I'll write 58 at its right place, right? So So because the 58 is greater than 14, I'll write it there. Next, the 24 is written in the right place. Next, 18 is just bigger than 14 is also written in the next location. Now I see 13. So the 13 is smaller than 14. So the 14 should be written after 13. So I write it in the right place, right? So after 13, I'm going to write 14. So the algorithm is simple. So I start, the 14 is the number which I'm going to write here. And then I'm going to remember the number. So as long as I see the numbers which are bigger than the 14, I write these numbers to the next location. So the 58 is returned to the next location, 24 is also returned to the next location, 18 is also returned to the next location. My while loop stops when I see a number which is smaller than 14. So I see 13. So I go to the next location. This 18 is already returned to the next location. In the place of 18, I just write 14. Okay, I repeat the algorithm. So when I go to the, let's say that t is 14, as long as I see a number which is bigger than the t, I write it on the next location. So I stop the first time when I see a number which is smaller than t, and then go and write in the next location the value of t. So repeat. So what we are going to assume is that in the ith iteration, the first I numbers are already sorted. I minus 1 numbers are already sorted, and then I am trying to insert the ith number. I start my I to be from 1 because if there is only one number, then that's already sorted. So when I start I, the first I minus 1 numbers already sorted. I am trying to insert the ith number in the right place. So what we do is that we take the, since the first I minus 1 numbers are already started, we start traversing to the left. So there is a j loop which starts with I minus 1. I remember that t is the number that I am going to insert, which is at d, which is the number which is exactly equal to fi. See, as long as this is a valid location which is greater than 0, it should not happen that j becomes minus 1. If all the numbers that I see are all greater than t, then I will come out of this loop with j is equal to minus 1. Okay. I repeat, if all the numbers that I have from a of 0 to a of I minus 1 is all of them are greater, then the j will be at the end of the loop will be 0, minus 1. So what we are basically doing is that we are looking at the sequence up to j minus 1 and trying to go backwards. When I try to go backwards, I will go backwards as long as the numbers that I am seeing are all greater than t. See, as long as I see a number which is greater than t, so what I do is that this fj is returned to the location of the next location. So fj is going to be returned to fj plus 1, and I decrease my value of j. I keep going to the left as long as the numbers that I see are greater than fi, and I stop the first time whether when I saw a number which is smaller than or equal to t, or I am out of the array, right? The j becomes minus 1. In that case, I have to just go and write the t to the fj plus 1th location. So fj number is smaller, but the next number is already returned to the next number. So fj plus 1th is the location where I have to write my t. I repeat this from I is equal to 1 to n minus 1. So at any point of time, I am assuming that the sequence from 0 to I minus 1 is already sorted. In the ith iteration, I am considering the afi. And at the end of the ith iteration, the sequence from 0 to I will be sorted. So the algorithm is simple. I start with the previous location. As long as I see a number which is bigger than the current number which is stored in t, I write this number to the next location. Keep doing this. I stop the first time when I see a number which is smaller than t, or I reach t, j is equal to minus 1. So once I come out of this loop, just go to the next location. I write it there because that is the right place. All the numbers to the right of j plus 1 are all greater than t, and all the numbers to the left of j plus 1 is smaller than t. Because the sequence was already sorted before this iteration, and I ensured that all the numbers to the right of j plus 1 is greater than t, and all the numbers to the left of j plus 1 are all smaller than t. I stopped the first time and the number was smaller. So this ensures that the sequence now will be sorted if the sequence was already sorted before I came to the ith loop. So let T of n be the number of comparisons done by the insertion sort algorithm. Then in worst case, when I insert the last element, assuming that the first n minus 1 numbers are already sorted, what may happen is that the number that I have right now may be the smallest number. In that case, I will end up doing n minus 1 number of comparisons, and then in the previous iterations I might have done T of n minus 1 number of comparisons. So in order to insert one number, assuming that the sequence is already sorted with n minus 1 numbers, b is exactly equal to n minus 1 plus the number of comparisons that are required to sort the n minus 1 numbers. So the T of n will be n minus 1 plus T of n minus 1. As seen before, this will be theta of n square. But this is only in worst case. If in the best case, what will happen is that the number of comparisons done by the insertion sort algorithm can be 0, because if the given sequence is already sorted in the increasing order, then the number of comparisons will be exactly order n, right? So the number of times the while loop will be executed is 0. Is exactly equal to 1. So the total number of comparisons this algorithm does will be exactly equal to n if the sequence is already sorted in the increasing order. So in summary, the number of comparisons done by the insertion sort algorithm will be between n and n square. So in summary, in this video I have seen three algorithms, namely bubble sort and selection sort and insertion sort. In the case of selection sort and the bubble sort, the number of comparisons in any case is theta of n square. Even if you give the sequence in the increasing order, the complexity is theta of n square. But in the case of bubble sort, the number of swaps that it was doing in the worst case was order n square, but the minimum number of swaps could be 0. But in worst case, the number of swaps was order n square. But in the case of selection sort, the number of swaps was decreased from n square to order n. So the number of swaps that the selection sort algorithm will have to do is any number between 0 and n. In this insertion sort, we try to avoid the swaps that we are doing. We just work with all the comparisons only, and unlike the bubble sort and selection sort algorithm, the best case complexity of insertion sort is 0. That means that if the given sequence is already in the increasing order, we may have to do only n number of comparisons. But in worst case, if the sequence is in the decreasing order, then we may have to again do order n square number of comparisons. In summary, so we can conclude that insertion sort is better than selection sort, which is better than the bubble sort algorithm. But in worst case, all the three will end up taking order n square number of comparisons, which is not the optimum way to solve the sorting problem. In the next videos, we'll study merge sort and quick sort, which using which we will be able to sort the numbers in order n log n.